Ladies and gentlemen, my name is Fomitchev-Zamilov. I am the founder of Maximus Energy Corporation, and some of you know me because of the radiation detectors that I make, neutron and gamma detectors. But I'm here to talk about my work on bubble fusion. And I recently observed significant neutron emission during cavitation of deuterated water, basically of heavy water in mineral oil. And I probably don't need to talk about bubble fusion much because you know what it is. The idea is you create a bubble inside a fluid, you expand the bubble, and then you collapse it. And if the bubble is filled with deuterium gas, under certain conditions, thermonuclear fusion might take place. So this is a version of inertial confinement fusion. And generally, when you speak about this subject, people say, well, it's not too interesting because you run into the same problems as with conventional inertial confinement fusion. And those problems, as you know, are instabilities. And truth be told, the same instabilities plague the bubble fusion approach because bubbles never collapse spherically. There is always inhomogeneity either in the acoustic fields or there are some different phases or surfaces. So as such, a cavitation jet forms that destroys the sphericity of the collapse. As such, if you talk to an academic about it, they say, well, fusion is not likely to happen. Well, luckily, I mostly disagreed with this idea, so I said, let me try and do it. So for several years, I worked on this, and here you see my experimental setup. I'll show you another picture that's a bit more easier to read. So inside here is my fusion reactor, which is basically a 6-inch stainless chamber that's filled with mineral oil. And through that chamber is connected to a pump and a Venturi nozzle, and Venturi nozzle is connected to a deuterium lecture bottle. And when the pump pumps the oil is saturated with nanobubbles that pass through the Venturi nozzle and then comes back to the chamber. And what you can see here in the bottom, there is a piezoelectric driver. And that piezoelectric driver generates acoustic waves that expand and collapse the bubbles inside the chamber. And here's a close-up of how the working fluid looks inside my chamber. So it's a mineral oil, and the reason it looks hazy here is because it's saturated with deuterium nanobubbles. And out here, I actually experimented with heavy water droplets. So this is an emulsion of heavy water droplets and mineral oil. And the reason glass is shattered here is because I was able to achieve very high amplitude of acoustic vibrations inside the chamber such that the glass got shattered. And I'll talk about that in a second. So when I started this work, for several months, I had no interest in results. Oh, and by the way, and this is the diagram of this whole setup. So once again, this is my reactor. This is my working fluid. And I have a piezoelectric transducer inside that measures, the acoustics inside the reactor. There is a piezo driver at the bottom, and right next to the reactor, there is a bunch of helium-3 tubes. Oh, and the previous speaker did a good job on describing some of the issues involving neutron detection. And if there is anything that I've learned, for the past 5 years, I've been working on neutron detection primarily. And for this experiment specifically, I used LND helium-3 field proportional counters. So 6 of them connected in a bank. And what you see here is a typical signal from a proportional counter. It's a negative voltage pulse in this case of a few millivolts in amplitude. And if this assembly or if this counter works right, you should be seeing a thermal neutron spectrum. And I can talk about neutrons all day long. In fact, I have a paper written on neutron detection best practices using helium-3 proportional counters that I'm going to reference at the end of my talk. So for many months, I did nothing but worked on neutron detection, learning everything about this process. And if there is anything that I've learned on how to measure neutrons using proportional counters. And when I started, I realized that the existing hardware and software is inadequate, so I developed my own. So I've built what I call automated nuclear lab, which is a system for rapid nuclear experimentation. So this is a data acquisition device. Here's a version of it too, and I'm going to have a poster session later today, and I can tell you more, about these devices that I make. But what it does, it allows you to connect a number of neutron or gamma detectors to it and capture the raw signal. Because it's important, when you run an experiment, to have access to the raw signal that you can analyze. You can run your pulse processing, you can extract your counts, extract your energy, and have all of the information at your disposal that you can scrutinize offline to where nobody can come to you and say, well, you've been counting noise. If there is any conclusion that I can draw before ending the presentation, is you always need to look at systematic errors. And you don't have access to your raw data, you cannot scrutinize the systematic errors. That's why capturing raw data is important. And I wrote software too. So because at the end of the day, you need access to your data. And this software that I wrote is called Pulse Counter. So it counts, it captures the raw signal that comes from the detector. It detects individual pulses, builds pulse height spectrum, gives you, count rate history. So it gives you, the complete, database of events that occurred, when you were monitoring neutron counts or gamma counts or whatever it is that you were trying to detect in a nuclear sense. And here I also need to mention that when we are measuring radiation, we're dealing with random processes. So it's never enough to take a single count, because if you take a single reading, what you're getting is a random number, because this is how nuclear physics works. This is how quantum mechanics works. Everything is a random number. So any singular reading you take can give you any value. It means nothing. So in order to compare counts, you need to compare your background to your experiment counts, or your experiment counts to your control counts, which means you need to acquire a bunch of count rate samples and build a Poisson distributions. And once you have your Poisson distributions, so here's a distribution for experiment, here's a distribution for background, only then you can compare them. And even then you still need to do a statistical analysis. For example, you can run student t-test and determine p-value that tells you, the probability that these distributions are the same, because you're not going to get, a lot of bars, and, visually you cannot tell, so you need to have a metric, and p-value and student t-test are the standard metrics, and they're all, automated in this software. So by building, this hardware and, writing the software, I was able to automate, the whole process of neutron monitoring, which allowed me to run thousands and thousands of experiments with instant conclusion. Do I have excess neutrons in my experiment or do I not? And this is how a typical result looks like. So red bars are background counts, and you can see they're all over the place, from 0 neutrons per minute to, let's say, 11 neutrons per minute. Then I turn on my reactor and I start logging these blue bars, which are all over the place too. And this line is a p-value trend. And because the p-value trend approaches 0, it's telling me that I'm experiencing a significant difference between background and experimental neutrons, and in this case, this difference is 40%. So this chart is telling me that my experimental counts of neutrons, when my reactor is on, are about 40% higher than the counts when the reactor is off, my background counts. So this is how I'm able to derive conclusions, quickly, using the software and the hardware that I developed. So I applied this to my neutron reactor. And by the way, this is the acoustic signal. So I was also capturing, the acoustic signal. And what you see here is a 20 kilohertz driving frequency of my piezoelectric driver. And these are, the high pressure spikes that I'm going to talk about in just a few seconds. So long story short, for a few months, I was running this reactor trying different things. I was trying primarily deuterium bubbles. Nothing was happening. I was trying different concentrations, different sizes of bubbles. Nothing was happening. So I introduced xenon, as Seth Putterman recommended. Nothing was happening. So I said I need to be more creative. So how about I add some heavy water to my reactor? Nothing was happening. So how about I add some, titanium deuteride powder to my reactor? So nothing was happening. But one day, something did happen. And what you see here is a neutron flux that I observed that was in excess of 1,500 neutrons per minute. And if you recall the previous presentations, most neutrons get absorbed in the reactor. So the actual flux was much higher than what I counted. But by comparison, background was under 30. So when my background was producing less than 30 neutrons per minute, I managed to count 1,500 or 1,700 in this occasion. So I said, well, this is interesting, but now I need to prove to myself that this is not noise that I'm counting. I need to be sure I'm counting real neutrons. So I look at my raw detector signal, and you can see it here. And I was astounded because usually it's just a flat line because you hardly see any neutrons. But out here, every spike is a neutron, and you see, countless and countless neutrons. So I zoomed in because I wanted to see, are those, real, negative pulses from a detector, or maybe this is noise. And this picture is interesting because it does have a little bit of noise. So each batch of undulations here is noise due to capacitive coupling between the neutron detector and the piezoelectric driver. But fortunately, this capacitive coupling is rather weak, so the signal it gives you is only like a few millivolts, whereas neutron pulses are on the order of 20 millivolts or over 20 millivolts. But this picture was fortuitous because I am able to see that I primarily get neutrons only when the sound is on, because when the sound is on, I get this capacitive coupling noise that I see on this plot. And when the sound is on, I see these spikes that correspond to neutron events. So this is how I can tell that what I see is neutrons, and they are in fact coincident with the acoustic excitation. But I wasn't happy with this noise, so for the next few months I worked on getting rid of this capacitive coupling and cleaning up my signal. Oh, and before I go into that, I want to show you another plot here. So this is a summary of counts of neutrons overnight. So for about about 12 hours I was counting neutrons, and this rate is, by the way, in counts per second. So maybe I was getting 1 or 2 neutrons per minute. But once I turn my reactor on, and these are red bars, so the count rate goes up tremendously. And then when I turn it off, it returns to background. I turn it on, and counts keep creeping up significantly, and they tend to increase as the reactor was operating. So in this mode, oh, and by the way, and this is one of the charts that correspond to a multiple neutron event. So there are several neutron events that are closely spaced together to the way it cannot be resolved by the detector. And I've seen quite a few of those. So over the next few months, my objective was to clean up the signal, make sure I don't get any noise from capacitive coupling or ground loops. And the objective was, of course, to collect a spectrum that looks like a thermal neutron spectrum. And eventually I succeeded. So I was able to run the reactor for a couple hours. And in those couple hours, the count rate was about 20 or 30 neutrons per minute compared to the background of 2 or 3, so 10 times in excess of background. But eventually, a perfect thermal neutron spectrum built up. And this is how I know what I counted is definitely neutrons. And that's why I advocate for using proportional helium-3 field counters, because at the end of the day, if you count neutrons, you should get a perfect thermal neutron spectrum. If you get something else, you're not counting neutrons. But if you do get a perfect thermal neutron spectrum, then it's a pretty clear indication. And this was the ultimate result I was looking for. And as I said, it took me 6 months to achieve it. And while I was doing this, I've run probably hundreds of different experiments. And here is some of the inexplicable results that I got. I already mentioned that my neutron counts tend to increase as the reactor was operating. So as the reactor was operating, counts increased from background to some over background value. And I expected when I turned the reactor off, the counts should return instantly to baseline. But on few occasions it did not happen. The counts instead gradually returned to baseline. And to this day, I don't know what to think of, because when I started this project, I was entirely expecting to observe conventional thermonuclear fusion. And if that thermonuclear fusion is assisted by acoustics, the second you turn off the acoustic drive, there is nothing to collapse your bubble, so there should be no neutrons. So yet, on more than one occasion, I observed this strange behavior where the signal gradually returned to baseline. And to this day, I don't know what to think of, but I figured I'll tell you about it, and maybe you'll have some ideas for me. But anyhow, at the end of the 6-month period, I was able to sustain my reactor in operational condition for 6 months. Meaning every time I turned on the reactor, I was able to observe and count these excess neutrons, build the thermal neutron spectrum. But there are some questions. And I guess the most unfortunate one is that I mixed this perfect working fluid by accident. So I mentioned that I tried a few things. And after experiments that didn't work, I was dumping my oil into a waste oil bucket. And at some point, I was running low on fresh oil, so I took oil from my waste bucket, put it in the reactor, and that's when I got my massive neutron counts. And that oil was heavily oxidized. So when I started, the oil was clear. There wasn't no color in it. Nothing. It was pretty clean. But the oil in my waste bucket was heavily oxidized from all the experiments that I ran. And also it had some content of copper soap because it also was greenish in hue. And copper soap must have been generated by copper gaskets that I used to seal my chamber. And because the water was present and sound was present, so it's feasible that copper soap, got formulated and dissolved in it. I also used borax around my reactor to screen background neutrons. So I was using borax not to defend myself from the reactor radiation, but to reduce the background. But some of those borax boxes were leaking, and I might have gotten some borax into my mixture. And I definitely had some DTO droplets because I did pour some DTO in my reactor, and I did pour some titanium deuteride powder that Alan Smith was very kind to make for me. So thank you, Alan, for the powder. I think it might have made all the difference. There were definitely some deuterium bubbles and definitely some small amount of hexadecane D40. And there was some xenon, but the xenon got evacuated. So what I also observed is that when I was pumping oil, the oil was acquiring significant electrostatic charge because the surface of the oil was getting curved inside the reactor, and my electrostatic meter got pegged off the chart. So electrostatic effect could have been significant too. I also operated my reactor at various pressures from 4 torr to atmospheric pressure of 760 torr. So I know pressure is not a factor. But most of my experiments were run at low-grade vacuum of around 20 torr. And also I observed neutrons from various concentration of this emulsion inside my reactor, from when it was completely opaque to when I just introduced 1 milliliter of that emulsion in the reactor. So somehow concentration doesn't have a significant role. But at all times I was using a 20 kilohertz driver, which I operated at in a pulsed mode with 0.2 seconds in a duty cycle. So this is what I know. Now let's talk about what I don't know. So I don't really know if my neutrons are from fusion. It could have been some other nuclear process, could have been spallation, or who knows what else. Because in order to determine or prove that this is a fusion neutrons, you actually need to measure their energy or observe fusion byproducts, and I've never gotten around to that point yet. So I also don't know whether my interactions took place in the bulk or on the surface. That's something also to think about, and might be on the surface because if the neutrons originated from the bulk, a lot of them would be absorbed by the oil itself. So for that reason, I did not have any moderator between the reactor and the neutron tubes. So the neutron tubes were as close as possible to the reactor, but without making contact with the reactor, because if there is a contact made, then you have this capacitive coupling and acoustic noise. So there was an air gap, which was filled with foam, but there was no moderator. And I also don't know why my neutron signal gradually increased with time, but it was always the case. I start my reactor and counts just keep increasing and increasing and increasing until I turned it off. And this kind of supports the idea that this was thermonuclear fusion, because what you expect tritium to be produced, right? And deuterium-tritium reaction is much higher probability. It's like 100 times, if not 1,000 times more likely to take place. So I take it as a indirect evidence that what I was saying is a thermonuclear reaction, because you start with deuterium, reaction rate is low, but as tritium builds up, and the reaction rate should accelerate. But it could be other explanations. But I certainly don't know why in some of my experiments, the neutron signal remained when I turned off the reactor, and it took it about 1 hour to return to baseline. But I did observe it several times, but most of the time, the neutron signal almost instantly disappeared when I turned the reactor off. So what I've tried, I tried. So once my mixture quit working and I started formulating hypotheses, what was it that made it work? So I thought maybe it was the DTO droplets. So okay, so for about a year, I worked with just heavy water droplets of different sizes, different concentrations, no excess neutrons. Then I thought, well, what did I overlook? And I realized, well, I overlooked titanium deuteride powder. So for the next 6 months, I worked with titanium deuteride powder and no heavy water droplets, just the powder, no neutrons. Then I said, well, let me try surfactants. Maybe this copper soap or borax that penetrated my oil. Maybe it created some surfactants. So I on purpose introduced surfactants. No effect. So I tried a bunch of things. And, to this day, 2.5 years later, I was not able to reproduce this significant nutrient signal, which I've gotten originally. And this is kind of a bummer, but I don't think I've exhausted all of the possibilities yet. And if there was any success in this, past 2 years, so I, with confidence, can say that I can reproduce this massive acoustic spikes. So recall this chart that I have here. So when you start with a sinusoidal driver, its amplitude isn't great. But when I introduce water droplets, I get these massive spikes. And these spikes are on the order of 10,000 atmospheres, sometimes more. Sometimes they're so strong they blow up my ultrasonic transducer. And sometimes they were so strong, they blew up the glass in the reactor. So if anything I've learned, I can reproduce the spikes, and I think they're important. So this is, what I'm thinking now. I think titanium deuteride, was crucial, but, so is heavy water. And I think that the reaction is caused by the cavitation jets. So when the bubbles expand and collapse, the instabilities result in these jets that penetrate the bubble, and I speculate these jets impinge on solid titanium deuteride particles suspended in my oil, and I think this is what drives the reaction, because the deuterium in titanium particles is compacted by these jets. So this is the working hypothesis. But I also suspect the deuterium nanobubbles are important, and I need to generate them again, because this is one thing I haven't tried in the past 2 years, and this is the thing I'm going to do when I come back from this conference. So on my to-do list is a couple things to try. I also, since I think the titanium deuteride is important, I intend to make the flange, the bottom flange to which the ultrasonic driver is affixed, out of titanium, and it's being made in the machine shop right now. And then I'm going to saturate the top layer with deuterium using thermal loading, and then I maximize the surface on which the bubbles could impinge. So the surface is going to be made rough specifically. And that's how I can test the hypothesis that it's the impact action of the cavitation jets impinging on the deuterated titanium surface. And in the meantime, I took some more of this powder that Alan made, and I made a pestle for it. And this is my ultrasonic driver. And I thought, what would happen if I just compact the powder through vibration? And this is an interesting chart, because the first reading I took gave me like 7 counts per minute. And then I started taking background, and background was significantly lower. So if you take this result at face value, you can say, well, I have a statistically significant above background count rate. But it's not true, because I didn't take enough counts during the experiment. I took only 1 count, and as I mentioned, the single reading you take could be anything. And I was just lucky that that singular reading was so high to where it was higher than all of the subsequent background readings. And this is nothing unusual. This is how randomness works. So when I took subsequent experimental readings, meaning this driver was energized, I didn't get high counts. So I didn't observe neutron counts from just acoustically compacting of dry titanium deuteride powder in a pestle. And I tried a number of those experiments. Okay. So I thought, well, maybe this powder is too rough, so let me make my own powder. So I spent next months, making my own powder. I started with titanium sponge, and I chose loading it, with deuterium under heating conditions, and I created, rather nice powder. So and I put some on eBay. So if you want to experiment with it, you don't have to make it yourself. But that's the powder I'm going to use in the next batch of experiments, because it's a lot finer. And I actually calculated the composition of it. It's pretty close to titanium 1.8 deuterium. So it's not quite titanium D2, but by the weight of the powder and by the amount of gas it consumed around a pound of titanium consumed almost 250 liters. So it was, quite an expensive enterprise, 250 liters of deuterium. But that's how I've gotten very close to, not quite titanium D2, but titanium D1.8. So I kind of have hopes for it. And of course, while I was doing it, I decided to take advantage of my hardware and software. So this is another neutron detector that I made that has 10 rather large tubes and has moderator on the other side. So there is no moderator between the chamber where titanium is being loaded. So it's just tubes there. And these are background counts, and these are counts when I was actually heating the titanium and I was absorbing the deuterium, and you can see that these counts are consistent with background. So I cannot say that neutrons aren't emitted. All I can say, I did not observe excess neutrons during this experiment. But that's what I like about the setup that I make, because it allows me to measure quickly and have a conclusive result quickly that I can scrutinize at a later time. So if you, I'm going to skip this. Oh, and of course a little bit of pitch. So since I reported my results on in Nature Scientific Reports, a bunch of people approached me and saying, why don't you put this project on WeFunder? So I did. So you can go and check it out there. But more importantly, I summarized my result in this publication. So you can read the observations of neutron emission during acoustic cavitation published in Nature Scientific Reports in May of this year. And I particularly recommend this reliable and neutron gamma detection paper that's available on my website, where I summarize the best practices for neutron detection using helium-3 proportional counter tubes, which could make an hour-long talk in its own right. And yeah, so that's it. Thank you very much.
Question? There are questions here. I don't know. Where's the microphone? Okay, Mathieu. Yes, go ahead. Mathieu.
Okay,
yes.
thank you. You show an increase of your software detection system and so on that is, for me, just a black box. Okay, but you show them always at the end of the time frame. Do you see after you stopped the hydrogen deterioration or the acoustic stimulation? Do you see?
Are you talking about this?
Yes. What is the shape of this anomalous? What you interpret as anomalous generation of neutrons after the stimulation or the deterioration has stopped?
So you can, first of all, you can see the results in real time. So as you run the experiment, you can see the counts in real time. So the count rate builds in real time and the spectrum builds in real time. So you see right there and then if you have any excess. But usually it's after the experiment. If the difference is small, it's usually after experiment you can tell the difference if you run the statistical analysis. But if the difference is large, you can see it right there and then. And you can also see the raw pulse, and you can inspect each individual pulse that was counted.
I got that. My question is, after the stimulation is stopped, what happens to this neutron count?
It remained consistent with background in the case of loading with deuterium. Yeah.
Okay. Anyway, Conrad, you have a question?
I'm not specialist in cavitation, but I remember the experiments made by Los Alamos people, several years ago. And the final result was the temperature in bubbles could be above even 1 million degrees. And it can be very easily understood in the term of DD reactions that can take place. What is the temperature in your case?
I have no idea, to be completely honest with you, because it's quite challenging, to measure the temperature. And all the papers I read on the subject, they say the plasma inside the bubble is opaque, so you cannot determine the temperature by direct observation. It's almost like indirect, and I don't have faith in indirect conclusions. And frankly, I don't believe in spherical collapse, because I tried working with it so much. So I think it's the mechanism of action is different. It's not uniform compression. It must be something else.
I understand. So the very interesting point is, first one, your bubbles are very small. They're nanobubbles. Compared to the other experiments, they were large one. And another point which is very interesting, you can see some neutrons only in the case if you have titanium gas inside or powder inside.
That's why
completely different compared to the previous experiments. So it is really interesting. Thank you.
Yeah, thank you.
I think we have to start. Last question, but no answer. Okay, go ahead.
As always, superb talk, Max. I guess I have a few. Sorry, John Paul.
Only the
The first thought is I hadn't seen that data before on that when you turned off the acoustic driver that the neutrons didn't go to background immediately, they decayed away. And I would encourage you to look at the decay constant if you can extract the decay constant and see if it correlates with diffusion of titanium, deuterium diffusion in titanium.
Good idea.
That would be a super interesting result.
idea.
And then the other thing is why were you not using a moderator?
Because the reactor was filled with oil to begin with.
Okay.
So if the neutrons originate from it, that oil already would have moderated
Gotcha.
the neutrons. Yeah.
The only thing I'll just say is like Max's neutron work is superb. So I think it'd be really instructive for the community to really lean into Max's expertise. He spent a lot of time on this, and these helium-3 tubes are going to be much, much better than CR39 for detecting neutrons. So that's my.
Okay, thank you very much.
Thank you.
And we have to thank again the speaker.